Hi, this is my video number 8. In this video I'll continue with the example of the limit of a sequence. Then I'll give you a related theorem, and as well I'll discuss on the monotone and monotone increasing and monotone decreasing. Okay, first let me recap the definition of the limit of a sequence. Yeah, so we say the limit of a sequence n goes to infinity, this is equal to L if given any epsilon positive, we can find n, some number n positive, such that the distance or the difference un and L less than epsilon less than epsilon for all n greater than n. Right? I've explained to you in the previous video the meaning of epsilon, the distance, and what is n greater than n, and so on. Now let me start with the continue with the example. So next example, that let's say we want to show that the limits n goes to infinity, n over n plus 1, this is equal to 1. Okay, so to do this, so we begin with the given epsilon positive, given any small number epsilon positive, then we take the difference between un and L. Our un is n over n plus 1, and our L is 1, so we have n over n plus 1 minus 1. Okay, that gives us we have n minus n plus 1 over n plus 1. That gives us basically negative 1 over n plus 1, and negative since we take the absolute value, so this gives us just 1 over n plus 1. And we know that if we decrease the number of denominator and decrease that, so the right hand terms or the terms after that will be greater than, so means that the left hand side is less than. So what we want to show that this is less than, all right, less than some number 1 over n. Okay, then remember that what we want to show that this we want to show is less than epsilon, and we want to choose what capital N is. So from there, of course, you can see that 1 over epsilon is greater than n. Yeah, just look at from that relation. This is, so then we can choose this is our n, so that all n, small n after the capital N is always satisfy the required condition. Okay, now having done that, we choose n equal to 1 over epsilon. Then what we have, so 1 over epsilon, this is come from this part here. Okay, then from there what we have, this is what we want to show, n over n plus 1 minus 1, this is less than 1 over n that we have shown in the previous step, and this is less than epsilon for all n greater than n. Okay, so then we can stress that therefore the limit n over n plus 1 n goes to infinity, this is equal to 1. So the main point again in this definition of the limit here, there exists n, so which means we need to find what n is. Okay, so this process shows that we can find n, which is 1 over epsilon, which with that choice of n, then we obtain for all n greater than those n, then the difference between terms or un and the limit is less than epsilon, which is satisfy the condition that we need. So let's consider another example. Let's say we want to show that the limit n goes to infinity, our un is 2n plus 3 over 3n plus 2. Right, this is equal to 2 over 3. So remember that our definition, I always write the definition here, given any epsilon, we can find n positive such that un minus L less than epsilon for all n greater than n. That's the definition of the limit. So we're going to use that definition. So the solution is, given any epsilon positive, a small number, then we need to find the capital N. Alright, so un minus L, we have un minus L, 2n plus 3 over 3n minus 2, this is our un, minus L, which is 2 over 3. Simplify this. So what we have here is that we have 2n minus 3 minus 2, 3n minus 2, 3n minus plus 2 over 3n plus 2, right? And this gives us, simplify those, we have 6n here minus 6n, that's cancel out. Then we have 9 minus 4, that you have 5, right? So we have 5 over, so we have 9n plus 6, 9n plus 6. Alright, then if we decrease the denominator, decrease the denominator, then the right hand side should be bigger than. So we have, this is less than, less than 5 over 9n, that give us 5 over 9n. Okay, then from there you can choose the what n, capital N is. Alright, the purpose is we want to make it less than epsilon. Okay, we want to make it less than epsilon. So in this case you can choose n is so we can choose 5 over 9 epsilon less than n, and then this is our capital N. Alright, now then we can choose our n from that part here. So choose n equal to 5 over 9 epsilon. Alright, So therefore we have 2n plus 3 minus 3n plus 2 minus 2 over 3. This is less than 9 over 9, not 5 over 9n. This is less than epsilon for all n greater than n. Now remember that in doing this, make sure that the inequality is always one-sided. Means that if we choose, we have a less than, we keep on doing less than. You cannot have somewhere in the middle you have like this, somewhere in the middle you have less than, and then you change to the greater than, and then you change to less than, and then you made up the conclusion from that. This is wrong. Okay, make sure if you have less than, you keep on doing less than till the end. So by doing this, ensure that the right hand side, the right hand side is that this term here, is always greater than left hand side. Alright, okay, so having done those with that two example, now let me give one theorem relating to the convergence of the sequence and the boundedness of the sequence. The convergence of the sequence guaranteed, I would say, guaranteed the sequence is bounded. So we have a theorem here. If the sequence un converge, then the sequence un itself is bounded. Okay, so let me give the general idea what we are doing here. First thing is that the our assumption that the un is converged. This part here, converge, it means that the limit of un, n goes to infinity, exists. Give it some number L. And what we want to show is that from that, having done that, or we know that L is converged, which means you can apply the definition given epsilon that exists, or you can find n positive such that un minus L less than epsilon for all n greater than n. That's the definition of the limit. And then what we want to show from there is that if this part satisfy, so which means we have un bounded, which means we want to show that those un less than some number m. So that's what we want to show. So those are the idea. Alright, so let me repeat that. This theorem says that we have our assumption that un is converged. Alright, un is converged, which means the limit exists. With the existence of the limit, we can use the definition of the limits. Alright, and then what we want to show is that we want to show the sequence is bounded, which means the absolute of un less than some numbers. Okay, now we prove from there, say that one is converged. Okay, let prove, let those sequence converge, which means we have limit of un, n goes to infinity, this is go to L. Then for every epsilon positive, okay, there exists n positive such that un minus L less than epsilon for all n greater than n. Okay, so from this part here, okay, from that part here, I rewrite those things. Therefore, we have un minus L less than epsilon. So we have from there that un minus L less than epsilon greater than minus epsilon, because we open up the absolute symbol there. Okay, for all n greater than n. And from here, what we have is that you can take out the L to the right of the inequality and as well as to the left of the inequality. So what we can have from there is that our un is less than L plus epsilon, or epsilon plus L, less than L minus epsilon. Okay, and then from here you look at this on the right side here, we have no problem because the symbol here is the positive. Yeah, so on the right side we have positive L plus epsilon, whereas on the right side here, what we want, we must have something like negative of L plus epsilon. That's what we want, because if we have right side less than L plus epsilon and left side we have negative of L plus epsilon, then again we can use the definition of absolute value. Alright, now to have this, you look at it from the number line, right? If you put a 0 here, of course the L plus epsilon on the right side, because epsilon is always positive, so we have L plus epsilon somewhere here. Alright, whereas on the other hand, for on the left side here, L minus epsilon, then definitely L minus epsilon is probably somewhere here. Yeah, if L is greater than epsilon, then we have somewhere. If L is negative, then of course it will be on the left side of those things. So we have here, this is L minus epsilon. If L positive, yeah, if L positive. Now, if we take the negative of L minus epsilon, so it will be somewhere here. So this will be minus L minus epsilon, that. So which means that, why? Because the negative is always on the left side of the positive numbers. Okay, so from there we can write, so therefore we have the L minus, so we have L minus epsilon here, L minus epsilon, this is less than minus L plus epsilon. Okay, just from here we take the negative and then we have this is, I can write this negative of L plus epsilon, just the same thing there. So I can put it there, so the statement is still correct. Alright, and we have less than un, and then we have less than L plus epsilon. So from there we rearrange this to make it more clearer. So we have L minus L plus epsilon less than un less than L plus epsilon. So therefore I can write absolute of un less than L plus epsilon, and this basically our m. Okay, so we have that the magnitude of un less than some number m. Now, having done that, we might have many of those. Yeah, we might have L somewhere L. Then we choose maximum of all those numbers. Yeah, so let m be maximum of u1, u2, and so on. Un, and last is that epsilon plus L, or L plus epsilon. Okay, take the maximum. Why? So let me explain those why. Because in the sequence, for example, if you consider the increasing sequence and bounded like this, okay, our L plus epsilon here, L plus epsilon, might be somewhere here, yeah, L plus epsilon. And then if we have any of those terms or element of that sequence bigger than L plus epsilon, maybe somewhere, yeah, we don't know, maybe somewhere there, bigger, this is, let's say, UN or what, U1 or UN, yeah, then we choose that the bigger number as our M. So let M is maximum with that. So then what we have is that UN is always less than M for all N. So therefore our sequence is bounded. Yeah, therefore UN is bounded. Okay, so I think the proof is quite clear. All right. So if you have a problem understanding, you can always message me. Yeah, always WhatsApp in the group, no problem. I will try to respond to whatever question you have. Okay. Then we have the theorem says that. Yeah, the theorem says that if the sequence converge, that means the sequence converge, we have UN bounded. Alright. So what about the other way around? If UN bounded, does it mean converge? Is it yes or no? For this, you can find the there are many examples you can see, like we have this kind of sequence, n plus 1. We know that this is approach to 1 or converge to 1. Okay, and also if you find the UN, which is n over n plus 1, definitely this is less than 1. So this is your M. So it's bounded. Alright, if you look at any other example, just give the same thing. And what about the other way around, which means if UN bounded, does the sequence converge? Now look at this sequence. I give you an example. Look at this sequence. So if you have like a sequence of cos n pi over 2. So if you list down this, what you have is that n is 0, so you got 0, cos 0 is 1, cos pi over 2, you have cos pi over 2, which is 0, alright, and then 1, 2, then pi, cos pi, we have minus 1, and then 0, alright, and then 1, and then again 0, and then minus 1, and then so on. That's kind of sequence that we have. So if you plot this, it's like what? We have 1, 0, minus 1, alright, and again 0, and then minus 1, and then 0, and then minus 1, and then 0, and then 1, and so on. So you can see this sequence actually, each of those elements will not exceed 1, will not more than 1, and also will not goes beyond than negative 1, or smaller than negative 1. So this is 1 and negative 1. So it's just a oscillate between 1 and -1. But at the same time, you can see as n increase, it's converge nowhere. Yeah, it's converge nowhere. So in this case, the sequence does not converge. So this is the example of the bounded sequence. The sequence bounded, but it is not converge. Yeah, this is an example of this sequence here, cos n pi over 2. This is bounded. Yeah, the bound for this is upper bound, and we have upper bound and we have lower bound, bounded, but not converge. But not converge. Okay, another example that we can have. Consider this example here. If you have -1 and +1. Yeah, if you list down this, the sequence is 1, -1, right? Yeah, and 1 and -1 and so on. That's our sequence. And then again, if you plot this, we have just 1, -1, 1, -1, 1, -1, and it's keep going like that. So the bound between 1 and -1, all right, but again it's converged nowhere. So again, in this case, we say this sequence is bounded but not converged. Yeah, but does not converge. So I hope you can understand the meaning of convergence, make a difference between the convergence sequence and the bounded sequence. Okay, now I'll give you the definition. All right, we say a sequence is increasing if, so look at the increasing sequence. Either converge or diverge, doesn't matter, but we need increasing sequence. We have here, this is U1, this is U2, you have U3, and so on. So you can see from here that basically we have U1 less than U2. Yeah, this is U1 here, U2 here. So U1 less than U2. No, sorry, this is 1, 2, 3. This is U1 here. This is U2. Then we have U3, and so on. Okay, so we can see U1 less than U2, less than U3, less than, and so on, and less than U, n, and less than UN plus 1, and keep going. So which means we say the sequence is increasing if UN is increasing if U1 less than equal to U2 less than equal to U3, and so on, less than UN less than UN plus 1, and so on. Okay, so we say this sequence is increasing, and we say the sequence n, we say UN is decreasing if, so look at the decreasing sequence. We look at the decreasing sequence. If you have a decreasing sequence, that, okay, so this is our n, 1, 2, 3, 4, and so on. And then what you can see, this is our U1, this is our U2, this is our U3, and so on. Now, you can see from this that U1 is always bigger than U2, always bigger than U3, and always bigger and bigger and bigger. Alright? So, which means we have, if U1 greater than equal to U2, greater than equal to U3, greater than, and so on, the UN greater than UN plus 1, greater than, and so on. So, the most important part here from these two relations, the increasing and decreasing, is this relation here. Yeah, and this relation here. So, which means if you want to show that UN increasing, so if we want to show that the sequence UN is increasing, what we need to show is that the UN always less than UN plus 1. Alright? On the other hand, if you want to show UN is decreasing, we need to show that UN is less than UN plus 1. Okay, now for these two cases or two terms that we not really introduce but give you the definition of increasing and decreasing. So we have the sequence, which is, let's say, UN is monotonically increasing, or monotonically decreasing. What does it mean? So, monotone increasing and monotone decreasing. So, it means that if monotone increasing, we have the sequence keep on increase. If monotone decreasing, our sequence keep on decrease. Alright? We don't have a sequence like this. We don't have this kind of sequence. Alright? So in this case, we don't say the sequence is monotone increase, or this part here decrease, then we say monotone decrease. So this, we don't call this. If the sequence increase and keep on increase, if the sequence is decrease and keep on decreasing as n increase, so this we call it as a monotonically decreasing sequence. So the same thing as if the sequence is keep on increase when we increase n, the sequence keep on increase when we increase n. So this case we call it as a monotonically increasing sequence. So now let me give you an example of how to show the sequence decrease or increase using these two relation here. Okay, you need to understand this. You need to memorize. I would say not really memorize. It's just if you understand the this concept here, then you don't have to memorize this. Just when you say increase, then basically you know what is this. Decrease, you know what is this. Okay, so let me give you an example. Let's say we consider this sequence 3 over n plus 5. Okay, show that show that this sequence is decreasing. Example. Oh, sorry. So this is your UN. That's your UN. This is your UN. Okay, 3/n plus 5. We want it decreasing, so that means we have UN. We want to show that UN less than equal to UN plus 1. Okay, so from here you can see this. If we decrease or increase the denominator, if we increase the denominator, which means the right hand side will be greater than. Okay. So the right hand side is less than. So we have this is less than decreasing. Just a minute. Do I get confused here? Oh, see. Just a minute. Sorry about this. This part here, this should be greater than. Should be greater than. Okay, and this should be greater than. This is what we want to show. Greater than. Alright. So we have that if we increase the denominator, for example, n plus 6, we fix the numerator. So what we have from there is that the right hand side here is less than the right hand side less than the left hand side. So this is less than. Alright. So the right hand side less than the left hand side, or in other words, the left hand side is greater than left hand side. And from this, what we can see, this is basically equal to 3 just n plus 1 plus 5. Correct? And what else, if you compare with that, our UN, and we have here n plus 1, this is basically UN plus 1. So therefore, from this relation, we show that UN is always greater than UN plus 1. So therefore, this sequence, therefore, this is for all n greater than 1. Yeah, for all n greater than 1. So this shows that the sequence decrease. So therefore, 3/n plus 5 is decreasing. Give you one more example before I stop this video. What about if you have this sequence, n squared plus 1? Okay, so let's say the question is we want to show this sequence is decreasing. So what we can do from here, our UN is n over n squared plus 1, and our UN plus 1 is n plus 1 over n plus 1 squared plus 1. Okay, this is our UN plus 1. So what we want to show that the sequence is decreasing. So which means we need UN greater than or equal to UN plus 1. So in order to do this, okay, let us assume that or suppose that, you can say that, suppose that the UN, those sequence n over n plus 1, n squared over n plus 1 is decreasing. We suppose that this sequence decreases. So which means if it decreases, so it must satisfy this relation. Okay, it must satisfy this relation. Now from there, you can simplify those things and then look at the final, the most simplified expression or inequality later on. Then if it's true, then it means your assumption is true. So let's do this thing. So from there, you can write this as a, of course, you can just multiply the left, the denominator to the numerator and so on. So we have here is, we have n, right? N plus 1 squared plus 1. Alright, this is greater than or equal to n plus 1 n squared plus 1. Okay, so from here you can expand this. We have n squared n, so you have n cubed plus you have 2n squared plus 1 plus 1, and then multiply by n, so we have a n, correct? Yeah, we have n and n plus 1. For 1, n and n plus 1. Okay, on the right side we have, if expand this, you have n cubed, we have n squared, we have n, and we have 1. Okay, so from there you can just cancel out those things. You can cancel out those things. So you can cancel out those things. So what we have basically 2n squared. We have n squared. So this is just n squared greater than positive. Yeah, and basically, and in fact, n squared is greater than 0, and it is true for all n, yeah, natural numbers. So what we have shown here, if this is not true, then we have n squared is a negative, which is wrong. For example, in the very same question here, we want to show that very same example, that n over n squared plus 1 is increasing. So of course this is not show. I change that determine, for example. Determine that sequence is increasing or increasing or decreasing. Okay, so if you want to say, let's say, suppose that sequence is increasing, which means we need un plus 1, un less than un plus 1. So we have our un is n over n squared plus 1, whereas for n plus 1, so n plus 1 over n plus 1 squared plus 1. This is our un plus 1. So for the increasing sequence, we need un less than or equal to that. So if you proceed this, you will have at the end you got n squared less than 0, which is impossible this to happen, because n is always positive. You got squared, again give you positive numbers, but from that assumption shows that this is a negative number, so definitely this give you a contradiction. So with that contradiction, it means that this sequence is not increasing, and in fact it is decreasing. So I hope you can understand from that. This example is quite clear to show that how to show the decreasing and increasing sequence. So differentiate between this thing, this and that. Yeah, we use the same un plus 1, but the difference is on our assumption. First, we assume that the sequence is decreasing. So what happened is that the last statement here, our statement is true. All right. Whereas if we assume the wrong way, yeah, n is increasing, this sequence is increasing, and later on we show the contradiction. So therefore, this is, I would say, a pretty nice example for you to look at. All right. So let me conclude what I have done for this video. Begin with the continuation of the example for the limits, and we look at the theorem of when the sequence converge, the limit exists, then the sequence is bounded, but the other vice versa is not happen. Means if the sequence bounded, then not necessarily the sequence converge. Then I also give you the definition of the increasing and decreasing sequence, monotonically increasing sequence and monotonically decreasing sequence with the enough example, I would say. Right. So with that, I thank you. See you in the next video. Bye.